Okay, so here we have Tarzan with a mass of 70 kilograms swinging from a 25 meter long vine, and we're told that the initial angle between the vine and the vertical is 50 degrees, and that Tarzan starts from rest. So Tarzan's going to swing down. It's going to be a circular path. Tarzan's going to swing down, and the first thing we're asked to find is his velocity when he's at the lowest point. So here's Tarzan at the bottom of the swing. Now this first question is actually not even a circular motion problem. This is a conservation of energy problem. This goes back to conservation of mechanical energy. So we're going to define our 0 point. Whenever you do conservation of energy involving potential energy, you need to have your 0 point set. So I'm going to do this with a red line. So this is going to be the 0 point right here. And the 0 point is where we measure h from. And if you remember back to conservation of energy, with potential energy, h is always the vertical height above the 0 point. So h is this height right here. So from the 0 point up to where Tarzan starts. Okay, so for number one, writing out our conservation of energy. Number one, we have potential energy initial plus kinetic initial equals potential energy final plus kinetic energy final. And there's no non-conservative forces doing work here. Sometimes kids will ask about the tension in the rope, which is a great question. The tension is a non-conservative force, but in this situation it's not doing any work because at all points the tension is perpendicular to the motion. So like if we look at Tarzan when he first starts swinging, his motion is this way and the tension is that way. So tension does no work because it's perpendicular to the motion, and that's true at all points. So my point is just that we're not going to have any work done by a non-conservative force. The only work being done as Tarzan swings down, the only work is done by gravity, and gravity is conservative. Okay, so up here is the initial. Take these away. So Tarzan does start with potential energy. He's above the 0 point. He starts at rest, so there's no kinetic. Kinetic initial is 0. And then he swings down, so down here is the final. There's no potential energy because he's on the 0 point, and he does have kinetic. So we're left with potential energy initial equals kinetic final, which is mgh equals 1/2 mv squared. The m's cancel out, and we get v equals square root 2gh. Now, we need to find the h, and I think I actually have a video on this already. Finding h is it's just a trig problem, a trig and geometry problem. So the way you go about this is you make a triangle up here, and this side of the triangle right here is cosine 50 times 25 meters, which is equal to 16.0697. And then the next thing to realize is that from here, from where the rope connects to the branch down to the lowest point, the total distance from there to there is 25 meters. So h, which is what we're looking for, this h value is going to be equal to 25 meters, the full distance, minus this part here, okay, which is 16.0697, which gives us an h equal to 8.9303. So now we go up here, finding the velocity at the lowest point. 2 times 9.8 and we figured out the vertical height that Tarzan starts from above his lowest point is 8.9303 meters, giving us an answer of 13.23 meter per second. All right, so that's the first question. Now the second question, the equation for centripetal acceleration is, and this is a tangential velocity, meaning his velocity there is tangent. At the lowest point, his velocity is tangent to that circular path. Centripetal acceleration, so solving number 2, the equation for centripetal acceleration is v squared over r, where that's a tangential velocity, which is our answer to number 1. So we plug in 13.23 meter per second. That's his velocity at the lowest point in the swing. And then the radius of the circle is the length of the vine itself, which is 25 meters. So this gives us a centripetal acceleration of 7.0 meter per second squared. And that's directed to the center of the circle, of the circular path. Centripetal accelerations are always directed to the center of the circular path, always to the center. Okay, third question, the net force on Tarzan at the bottom of the swing. So this is, we'll go over here, question 3. So we know that F net force, is always equal to mass times acceleration. Whenever an object is in a circular path, the acceleration is a centripetal acceleration. So this is a centripetal acceleration. When Tarzan's at the lowest point in the swing here, he's in the midst of a circular path, so the acceleration that he has is a centripetal acceleration. And we have the centripetal acceleration at the lowest point as 7 meter per second squared. And we know that Tarzan's mass is 70. So we go mass times acceleration gives us a net force of 490 newtons. And for question number 4, the centripetal force, well, up here we have F net equals mass times centripetal acceleration. If the acceleration you're talking about is a centripetal acceleration, then that means the force is a centripetal force. So for question 4, we just go centripetal force is mass times centripetal acceleration. So these two questions, questions 3 and 4, were just meant to make you think, about net force and centripetal force. Basically, the net force on Tarzan is the centripetal force. So it's the same exact thing. This just comes out to be 490 newtons. The centripetal force is the net force. Okay, and then the last question, we'll make some room here. All right, so the last question, finding the tension in the vine at the bottom of the swing. So here's the swing right here. Tarzan swings down. When he's at the lowest point, so here's Tarzan at the bottom of the swing, there are two forces acting on Tarzan. We have gravity pulling him down, and then we have the tension in the vine pulling him up. And for circular motion problems, you always want to make the center of the circle, so up here this dot represents the center of the circle, always make that positive. And the reason you want to make that positive is because the centripetal acceleration always points there. Centripetal acceleration always points to the center of the circle, so it's nice to have your acceleration as a positive value. All right, so what we're going to do is we're going to sum the forces for Tarzan. So here we have our free body diagram. So basically we're going to do free body diagram, sum the forces, and then solve. So the summing of the forces, T minus mg equals ma, and this acceleration is a centripetal acceleration. So basically, we're back to over here. F net equals ma. T minus mg, that is F net. And that is the centripetal force. But looking at it the way I have it boxed, what we can do is we can take this and solve it for tension, which is what we're looking for. The tension in the vine is going to be mass times centripetal acceleration plus mg. So we can factor out the m, like that. So tension is going to be 70 kilograms. And then our centripetal acceleration, we already solved for that. I mean, you could just do v, you could just go v squared over r, because that's the equation for centripetal acceleration. But we already did that in question 2, and we found the centripetal acceleration at the lowest point to be 7 meter per second squared, and gravity is 9.8. Don't make gravity negative. Up here, we already called gravity negative, so don't make it negative down here. And then we punch this into our calculator, and we get 1,176.1 newtons. That's the tension in the vine. And if you subtract mg from that, if you take 1,176, subtract away mg, you're back to 490, which is the net force or the centripetal force. So the thing to remember is there's two forces acting on Tarzan. The sum of them, taking into account that mg is minus, the sum of these is the net force, which is the centripetal force. But tension is larger than mg, which makes sense because Tarzan is accelerating towards the center. You know, as soon as he passes through the lowest point here, he's going to be on his way up. Tension is larger than mg.